And now in this lecture we'll answer on two questions. In the first question we will find out the radius of this circle that is described by the right triangle ABC. And in the second question we will find out the area of the blue right triangle that is inscribed by a quarter circle. So we start with the first question. In the drawing we have a right triangle ABC, side AB equals to 8 units, angle ABC equals to 90 degrees, and we also know that side BC and side AC are integers, and we want to find out the radius of this circle that is inscribed by the right triangle ABC. So first of all we will define side BC as A, and we will define side AC, the hypotenuse AC, is B, and we will implement the Pythagoras theorem on the right triangle ABC. So in the right triangle ABC, according to the Pythagoras theorem, PT is a relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AB squared plus BC squared. Repeat again, in the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. According to our definition, AC equals to B, is equals to B, therefore AC squared is B squared AB equals to 8 units according to what is given in the question. So AB squared is 8 squared, that is 64, plus BC squared. According to our definition, BC equals to A, so BC squared is A squared. Here we subtract A squared from this equation number 1, and we get that according to equation number 1, B squared minus A squared equals to 64. And use the algebraic identity that states that B squared minus A squared equals to B plus a times b minus a, and it is equal to 64 according to equation number 1. So actually, according to what is given in the question, AC and BC integers, and according to our definition, AC equals to B and BC equals to A, so P and A are integers. And A is the length of the perpendicular, and AC and B is the length of the hypotenuse. So actually A and B are lengths, and as lengths, they must be a positive number. So actually, you can say that the A and B must be integers and also must be positive. That is to say, A and B are positive integers, A and B are positive integers. So if A and B are, they are positive integers, it means that B plus A must be greater than B minus A. This is from one side, but also B is the hypotenuse, and the hypotenuse is greater than any other perpendicular, so B must be greater than A. And if we subtract from this inequality A, we get that B minus A is greater than 0. B minus A is greater than 0. So here B plus A, B is integer and A is integer, B is positive integer and A is positive integer and B is positive integer, therefore A plus B will be also positive integers. And here again B is positive integer and A is also positive integer, and we know that B minus A is a positive number, therefore it must be also a positive integer, because when you subtract two positive integers from each other, if the result is a positive number, it must be a positive integer. Okay, so we actually arrive to the conclusion that b plus a are positive integers and b minus a are also positive integers. So, according to equation number 1, we have b plus a, that is a positive integer, and when you multiply it by b minus a, that is also positive integer, the result must be 64. So, which two positive integers we have that if we multiply one by each other, the result will give us 64. There is not a lot of possibilities here. So I write down all the possibilities of two positive integers that if you multiply one by each other, one by the other, you will get 64. So the first pair will be 1 times 64, that is 64. The second couple will be 2 times 32, that is also 64. The third couple of positive integers will be 4 times 16, that is also 64. The fourth couple of positive integer will be 8 times 8, that is also 64. The fifth couple will be 16 times 4, that is 64. And the sixth couple will be 32 times 2, that is 64. And the last couple will be 64 times 1, that is also 64. So we have 7 possibilities, which we multiply two positive numbers, two positive integers by each other, and the result is 64. But because of the fact that b plus a must be greater than b minus a, it means that the first column must be greater than the second column. Okay? That is to say, 1 is not greater than 64, so this is not possible because b plus a is not greater than b minus a, so we'll cancel this possibility. 2 is not greater than 34, so we'll cancel this possibility. 4 is not greater than 16. 8 is not greater than 8. And 16 is greater than 4, so this possibility is good possibility. 32 is greater than 2, therefore this is a good possibility. And finally 64 is also greater than 1, so this is a good possibility. So we left only with 3 pairs of numbers that could be our solution to the problem for b plus a and b minus a. 16 and 4, 22 and 2, and 64 and 1. Okay, in the next step we will add the two positive integers together in order to find out which result we'll get. So here we will add b plus a to b minus a, and we'll get here that b plus b is 2b and a minus a is 0. So if we add the two numbers, we must get an even number, because 2b is a positive integer, therefore 2b must be an even number. Now we will add the two numbers together, and only if the result will be even number, it will be a good solution to the problem. Otherwise, it is not a good solution, we cancel the solution. So here 16 plus 4 is 20, 20 is an even number, so this is a good possibility. 32 plus 2 is 34, 34 is an even number, so this is a good possibility for the answer to the question. And 64 plus 1, it is an odd number, it is not an even number, therefore this is not a good possibility. We'll cancel this solution and we left only with two possibilities. The first possibility is that b plus a is 16 and b minus a is 4, and the second possibility is b plus a is 32 and b minus a is 2. Okay, so we will write down. Now we will find out, actually found out the values of b plus a and b minus a, and we actually want to find out the value of a and b in each solution. So here we found out that according to the first solution, b plus a equals to 16 and b minus a equals to 4. This is the first solution. In the second solution, we found out that b plus a is 22 and b minus a is 2. Okay, so those are the two solutions that are possible. Now we'll find out the values of a and b in each solution. So here we'll add the first equation to the second equation. B plus b is 2b, a minus a is 0, so we got that 2b equals to 16 plus 4, that is 20. So 2b equals to 20. We divide this equation by 2, and we get that b equals to 10 units. And according to this equation, b plus a equals to 16. We subtract b from this equation, and we get that a equals to 16 minus b, and we already found out that b equals to 10 units, so a will be equal to 16 and b is 10, so 16 minus 10 is 6. So in conclusion, we found out that the value of A is 6 units. Here A equals to 6 units and the hypotenuse B is 10 units. This is according to the first solution. And according to second solution, we will add equation number 1 to equation number 2 here. And we'll get that b plus b is 2b, a minus a is 0, and 32 plus 2 is 34. We divide this equation by 2, and we'll get that b equals to 34 over 2 is 17. So the hypotenuse equals to 17 units, and a, according to this equation, b plus a equals to 32. We'll subtract b from this equation and we'll get that a equals to 32 minus b. A equals to 32 minus b. So a equals to 32 minus b, but b equals to 17, so it is 32 minus 17. 32 minus 17 is 15. So according to the second solution, the perpendicular A equals to 15 units and the hypotenuse B equals to 17 units. This is the second solution. Now we'll draw the two solutions that is possible for A and B. According to the first solution, we have here a right triangle, triangle ABC. This is the right triangle, triangle ABC. It is given as the question that AB equals to 8 units. We just right now found out that BC equals to 6 units and the hypotenuse AC equals to 10 units. Inside this right triangle we have a circle that is described by triangle ABC, this triangle. So we have to find out the radius of this circle that is inscribed by this specific right triangle, triangle ABC. Okay. So we will define the radius of this circle that is described by triangle ABC as capital R. The center of the circle is here at point O. And we want to find out the radius of this circle that is described by this specific triangle, triangle ABC. So this is the first solution that is possible. But we have also the second solution for the right triangle, triangle ABC. Here, triangle ABC can be also this triangle. is given as the question that AB equals to 8 units. We found out that the perpendicular BC equals to 15 units, and the hypotenuse AC equals to, this is B, equals to 17 units. Inside this right triangle we have a circle that is inscribed by this right triangle, triangle ABC. And actually we want to find out the radius of this circle that is inscribed by triangle ABC. Okay, so we haven't finished the question yet because we have to find out the radius of the circle that is inscribed by the right triangle ABC in each case. Okay, so in order to find out the radius of this circle that is inscribed by triangle ABC, we will take a right triangle ABC. In this right triangle ABC, side AB equals to A. So we solve the problem for any right triangle that blocks a circle inside it, and then we will implement the solution for our two right triangles. So here, so this is triangle ABC, that could be any triangle. Okay, so side AB equals to A units, side BC equals to B units. And the hypotenuse AC equals to C units, according to our definition, of course. Okay, inside this right triangle ABC, we have this circle with radius that is equal to capital R. The center of this circle is at point O. So here we have rule number 1 here, but we know that tangent BC is perpendicular and tangent BC is tangent to this circle at point M. Point M is the point of tendency. Tangent AB is tangent to this circle at point N. So I write here that M and N are the point of tendency, of tangencies of the tangents with the circle. And we will define the point of tendency of the hypotenuse AC with this circle as point L. We will join points O and N together by a straight line. Point O is the center of this circle. Point N is the point on the circle itself. Therefore, line segment NO is the radius of this circle, because this is the definition of a radius. this line segment that starts from the center and ends at point N, that is the point of the circle itself. So this is the radius of this circle. This is equal to capital R. We have here rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius ON, it is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever we have a radius which is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO according to rule number 1, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we have the radius OM. Here, the radius OM, it is drawn to the point of tendency. That is to say, it is drawn to point M. This is the point of tendency of tangent BC with this circle, and whenever we have a radius which is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So actually, inside quadrilateral NOBM, we have 1, 2, 3 right angles. And you know that the sum of the angles in any quadrilateral is equal to 360 degrees. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, the fourth angle, that is to say angle NOM, must be also equal to 90 degrees. So we found out that inside quadrilateral NOBM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. Okay? So we relate to quadrilateral NOBM as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. NO equals to BM, but we know that NO equals to R, therefore BM must be also equal to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. OM equals to NB, but we know that OM equals to R, so therefore NB will be also equal to R. And what is the length of AN? From the drawing, it is very easy to see that AN equals to AB minus NB. Again, AB minus NB equals to AN. So AN equals to AB, that is A, minus NB, that is R. So in conclusion, we found out that AN equals to A minus R. Likewise, we find out the length of line segment MC. From the drawings, it is very easy to see that MC equals to BC minus BM. BC minus BM equals to MC. BC is B and BM is R. So in conclusion, MC equals to B minus R. Okay, so in conclusion, we found out that MC equals to B minus R and AN equals to A minus R. Okay, in the next step I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. I repeat again, the lengths of two tangents from a common standpoint to a circle are equal. So if you focus on the common standpoint point A, we have here two tangents to this circle, tangent AN and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AN equals to AL, according to rule number 2. But we already found out that AN equals to A minus R. Therefore, AL will be also equal to A minus R because they are equal to each other, according to rule number 2. Likewise, if we focus on the common standpoint point C, from the common standpoint point C, we have two tangents to this circle, tangent CM and tangent CL. And according to number 2, they are equal to each other. That is to say, CM equals to CL. CM equals to CL, but we've already found out that CM equals to B minus R. Therefore, CL will be also equal to B minus R. So in conclusion, we found out that CL equals to B minus R and AN equals to A minus R. So actually the hypotenuse AC from the drawing, it is very easy to see that the hypotenuse AC equals to AL plus LC. AL plus LC. Again, the hypotenuse AC equals to AL plus LC. So, according to our definition, the hypotenuse AC equals to C. So we substitute AC by C. AL equals to A minus R, according to what we already found out. So we substitute AL by A minus R, and LC or CL equals to B minus R. So we substitute LC by B minus R. So in conclusion, we found out that C equals to A plus B minus R minus R. That is to say, C equals to A plus B minus R is minus 2R. So C equals to A plus B minus 2R. Here we will add 2R to this equation, and we'll get that 2R plus C equals to A plus B. Here we subtract C from this equation, and we'll get that 2R equals to A plus B minus C. Here we divide this equation by 2, and we get that R equals to A plus B minus C over 2. So we actually found out a general formula to find out the radius of any circle that is inscribed by a right triangle, triangle ABC. Now we can use this formula in order to calculate the radius of those two circles that are inscribed by the right triangles, triangle ABC. So according to this formula, we got that R equals to A plus B, that is the sum of its perpendiculars, minus C, that is minus the length of the hypotenuse, over 2. Okay? This formula that we found, it is all in any right triangle ABC that blocks a circle inside it. Therefore, we can use this formula in order to find out the radius of these two circles that are inscribed inside the right triangle, triangle ABC. So according to this formula, we get that the radius of this circle that is described by this specific right triangle will be equal to A is 8 plus B is 6 minus C is 10 over 2. 8 plus 6 is 14, and 14 minus 2 is 4, and 4 over 2 is 2. So I found out that the radius of this circle equals to 2 units. We use the same formula in order to find out the radius of this circle. The radius will be equal to A plus B, that is 8 plus 15, minus C, that is the hypotenuse, that is equal to 17 units, over 2. 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So the radius here equals to 3 units. So in conclusion, we found out that we have here two solutions to the problem, and the radius of this circle that is inscribed by the right triangle, triangle ABC, it is equal to either 2 units or 3 units, and that is the answer to the question. Okay, the radius of this circle that is inscribed by the right triangle, triangle ABC, could be equal to either 2 units or 3 units. Okay, that is the answer to the question. We finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in 2 different methods. In the drawing, we have a quarter circle. We know that side OB equals to 2 units, AD equals to DO. Here, inside this quarter circle, we have the right blue triangle, triangle BCD, and get BCD equals to 90 degrees. And we want to find out the area of this blue right triangle, triangle BCD. Let's start with the first method. We know that AOB is a quarter circle, therefore here this angle AOB must be equal to 90 degrees. And point O is the center of the quarter circle. Okay? Point O is the center of the quarter circle, and the radius of the quarter circle OB equals to 2 units, and the radius is also equal to AO, that is also 2 units. So here we can write down that AO equals to OB, and they are both equal to 2 units, that is the radius of the quarter circle. Okay, AO equals to OB is equals to 2 units, but AO also equals to AD plus DO. AD plus DO equals to AO. Here you can write down that AD plus DO equals to AO. And if we define AD as X, AD equals to DO, so DO will be also equal to x. So it will be x plus x, that is equal to 2 units. X plus x is 2x, so 2x equals to 2 units. We'll divide this equation by 2, and we'll get that x equals to 1 unit. So here, DAD equals to x, that is equal to 1 unit, and DO is also equals to x, that is also equals to 1 unit. Okay? In the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle. We will extend the radius BO by straight line until it touches the circle, and we will define the touching point of the extended radius BO and the circle as point P. Point O is the center of the circle, point P is the point on the circle itself. This is exactly the definition of a radius. So PO is the radius of this circle, that is equal to 2 units according to what is given as the question, because the radius of the circle is the sum of the radius of the quarter circle. They have the same radius also, of course. In the next step, we will extend side CD by a straight line until it touches the circle. And here, suppose that the extended side CD touches the circle in this point, point X. Okay? So here we created a peripheral angle BCX. Angle BCX is a peripheral angle, and we know that peripheral angle BCX equals to 90 degrees according to what is given as the question. So peripheral angle BCX equals to 90 degrees according to what is given as the question. But we know that we have the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. And here BP is the diameter of the circle. I'll write it down. PB is the diameter of the circle, why? Because chord BB passes from the center of the circle, therefore it must be the diameter of the circle. So according to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, it means that when we extend side CD by a straight line, it must touch point P. Otherwise, the peripheral angle BC x that is equal to 90 degrees will not rest on the diameter of the circle. That is to say, point X must merge with point P. In order that peripheral angle CBX will be equal to 90 degrees according to the rule that I mentioned, point X must merge with point P. Otherwise, peripheral angle BCX that is equal to 90 degrees will not rest on the diameter of the circle that is BP. So here, therefore, we arrive to the conclusion that point X must merge with point P, and when we extend side CD by a straight line, it must touch point P, or it must pass for point P. That is the only way that peripheral angle BCX will rest on the diameter of the circle that is PB. Okay? And here PB is the diameter of the circle. PB is the diameter of the circle. It is absolutely a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line PB at point O, here, the sum of the angles here must be equal to 180 degrees. Which angles we have here? At point O on the upper side of PB we have 90 degrees plus this angle, angle AOB. In total, the sum of those two angles must be equal to 180 degrees. That is to say, this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of PB at point O to 180 degrees. This angle must be also equal to 90 degrees. Okay? So we'll focus on the right triangle POD. We'll implement the Pythagoras theorem on the right triangle POD. On the right triangle POD, by PT is the relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is to say, the hypotenuse is PD, so the square of the hypotenuse is PD squared. That is equal to DO squared plus PO squared. I'll repeat again. According to the Pythagoras theorem, PD squared equals to DO squared plus PO squared. So PD squared equals to DO squared. DO is 1, so DO squared is 1 squared, that is 1, plus PO squared. PO is 2, so PO squared is 2 squared, that is 4. So in conclusion, we found out that PD squared equals to 1 plus 4, that is 5. Here we take a root out of this equation and we get that PD, the hypotenuse PD equals to the square root of 5 units. PD equals to the square root of 5 units. So we repeat on the same process on the right triangle DOB. In the right triangle DOB, according to the Pythagoras theorem, by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is dB, therefore the square of the hypotenuse is dB square. That is equal to the sum of the squares of the perpendiculars, that is to say it is equal to dO square plus OB square. Okay, and then the Pythagoras theorem, dB square in the right triangle DOB, dB square equals to dO square plus OB square. Okay, so dB square equals to dO square. dO is 1, so dO square is 1 square, that is 1, plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, I found out that the dB square equals to 1 plus 4, that is 5. Here we'll take a root out of this equation and we will get that dB, the hypotenuse, equals to the square root of 5 units. So we can write down here that dB equals to the square root of 5 units. In the next step, we will extend the radius AO by a straight line until it touches the circle. At this point, we will define the touching point of the extended radius AO in the circle as point Z. Actually, point O is the center of the circle. Point Z is a point of the circle itself. This is exactly the definition of a radius. That is to say, the radius OZ equals to 2 units, according to what is given as the question. In the next step, we will implement rule number 1 in our drawing. Rule number 1, this with 2 chords that intersect with each other inside the circle. So if we have this circle, so here, if we have here a chord AB, this is called AB, that intersects with chord CD, this is called CD. At point O is the intersection point of chord AB with chord CD. Then the following equation is true, that AO times OB equals to CO times OD. In any circle, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, so here we can implement rule number 1 in our drawing, because in our drawing we have chord AZ. This is chord AZ. Intersects with chord CP at point D. Point D is the intersection point of chord AZ with chord CP. Therefore, according to rule number 1, we get that AD times DZ equals to CD times PD. Okay, repeat again. According to rule number 1, AD times DZ equals to CD times PD. So here, AD equals to 1 unit, DZ equals to 1 plus 2, that is 3, and it is equal to CD, that is the missing line segment, times PD. PD equals to the square root of 5 units. So in conclusion, we found out that 3 equals to square root of 5 times CD. Here we divide this equation by square root of 5, and we get that CD, the missing line segment CD, equals to 3 over square root of 5 units. So we can write down here that CD equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. On the right blue triangle, triangle DCB, by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is dB, therefore the square of the hypotenuse is dB squared, and it is equal to the sum of the squares of the perpendiculars. It is equal to dC squared plus CB squared. Repeat again. In the right triangle, triangle DCB, according to the Pythagoras theorem, dB squared equals to dC squared plus CB squared. We have already found out that dB equals to the square root of 5 units, therefore dB squared is square root of 5 squared, that is 5. It is equal to dC squared. dC is 3 over square root of 5, so dC squared is 9 over 5. 9 over 5 plus CB squared. So in conclusion, we found out that 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation, and we find out that 5 minus 9/5 equals to CB squared. Here we will multiply 5 by 5, and then we divide it by 5 in order to have a common factor with this expression. 5 times 5 is 25. Minus 9 over 5 equals to CB squared. Here 25 minus 9 is 16 over 5 equals to CB squared. Here we take out of this equation, and we get that CB equals to the square root of 16, that is 4 over square root of 5. So we found out the value of CB. CB is 4 over square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area of triangle DCB this right blue triangle will be equal to the base of the triangle that is DC times the height to the base that is CB over 2. I repeat again, the area of the right blue triangle DCB equals to the base of the triangle that is DC times the height of the base that is CB over 2. Okay, so here DC equals to 3 over square root of 5 units. Here CB equals to 4 over square root of 5 units, all divided by 2. Okay. Here we get that 3 times 4 is 12. Square root of 5 times square root of 5 is 5 times 2. So 12 over 2 is 6 over 5. So we found out that the area of the right blue triangle DCB equals to either 6 over 5 square units, so in terms of numbers it is equal to 1.2 square units. So we finished with the first method. In the next step I will present to you the second method. Here we already found out that angle AOB equals to 90 degrees. In the first method, AD equals to 1 unit, DO also equals to 1 unit. Here we will complete the quarter circle to a semicircle. And we will extend the radius BO by a straight line until it touches the semicircle. And you will define the tangent point of the extended BO and the semicircle as P. Point O is the center of the semicircle, point P is the point on the semicircle itself, therefore PO is the radius of the semicircle that is equal to 2 units, according to what is given as the question. Here we have already found out that if we extend, in the first method, that if we extend side CD by a straight line, it must touch the circle. Touch the circle at point P. Okay, so I will not repeat on the explanation. We did it in the first method. We have already found out that angle DOP equals to 90 degrees. We have already found out that in the first method that PD equals to the square root of 5 units, and here DB equals also to square root of 5 units. We'll define angle DPO as theta. In the right triangle DPO, angle DOP equals to 90 degrees. Angle DPO equals to theta, therefore this angle must be equal to 90 degrees minus theta. In order to complete the sum of the angles, 280 degrees in the right triangle, it must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta equals to 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. So if we focus on the right triangle BCP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reasons that in triangle POD, this angle equals to 90 degrees minus theta. So in the next step, we will prove that the right triangle POD is similar to the right big triangle PCB. So we focus on the right triangle POD. in the right triangle, triangle PCB. And we prove that those two right triangles are similar to each other. When they are similar to each other, first of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So, angle DOP, this angle equals to angle BCP, this angle repeat again, angle DOP equals to angle BCP equals to 90 degrees. In addition, this is a common angle that belongs to both triangles, so this angle equals to itself. So angle DPO equals to angle CPB. It is equal to theta. So angle DPO equals to angle CPB equals to theta. It is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees from theta, therefore they are equal to each other. Here, angle POD equals to angle CBP, and they are equal to 90 degrees from theta, therefore they are equal to each other. So actually, found out that all three angles of triangle POD can go into all three angles of triangle PCB, therefore triangle POD is similar, this is the sign of similar, to triangle PCB. According to angle similarity rule. Okay. For the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is equal to PO over PC. Okay, so we conclude that PD over PB equals to DO over CB equals to PO over PC. So here PD equals to the square root of 5 units. PB equals to 2 plus 2, that is 4. DO equals to 1 unit. CB is the missing line segment, so we leave it as it is. And it is equal to PO. PO is 2 over PC. PC equals to the square root of 5 units plus DC. So in conclusion, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Here we derive from this big equation the first equation, the square root of 5 over 4 equals to 1 over CB Here we multiply this equation by C. We cross multiply this equation, and we get that square root of 5 times CB equals to 4. We'll divide this equation by square root of 5, and we'll get that CB equals to 4 over square root of 5 units. So we can write here that CB equals to 4 over square root of 5. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. On the right blue triangle, triangle DCB, by PT, the square of the hypotenuse equals to the sum of the surface of the perpendiculars, that is to say dB square equals to DC square plus CB square. Okay, so dB square equals to DC square plus CB square. CB is 4 over square root of 5, so CB square is 16 over 5. So in conclusion, if I know that dB square equals to DC square plus 16 over 5, dB is square root of 5, so dB square is 5. That is equals to DC square plus 16 over 5 so here we will subtract 16 over 5 from this equation, and we get that DC square equals to 5 minus 16 over 5 . So here we'll multiply 5 by 5 and then we'll divide it by 5 in order to have a common factor of this expression, and we get that DC square equals to 5 times 5 is 25 minus 16 over 5. And so DC square equals to 25 minus 16 is 9 over 5. Here we take out of this equation and we'll get the DC equals to the square root of 9 is 3 over square root of 5. So in conclusion, we found out that DC equals to 3 over square root of 5 units. Now it is very easy to see and to find out the area of the blue right triangle, triangle DCB, the area of the blue right triangle, triangle DCB will be equal to the base of the triangle that is DC times the height to the base that is CB over 2. I repeat again, the area of the right blue triangle, triangle DCB equals to the base that is DC times the height to the base that is CB over 2. So DC equals to 3 over square root of 5 units, times CB is 4 over square root of 5 units, divided by 2. So here we have 3 times 2 is 12, square root of 5 times square root of 5 is 5, times 2. 12 over 2 is 6 over 5. So in conclusion, we found out that the area of the blue shape, the blue right triangle DCB, equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. We finished with the second method. In the next step, we will summarize the lecture. Okay. We start with the first question, of course. In the drawing, we have a right triangle ABC. We know that side AB equals to 8 units, and we also know that BC and AC are integers. Inside this right triangle ABC, we have a circle that is inscribed by the triangle, and we want to find out the radius of this circle that is inscribed by the right triangle ABC. So we define side BC as A, side AC, the hypotenuse is B. We implemented the Pythagoras theorem on the right triangle ABC. AC square equals to AB square plus BC square. AC is B, AB is 8, so AC is B, so AC square is B square. AB is 8, so AB square is 8 squared, that is 64, plus BC square. BC is A, so BC square is A square. We subtracted A square from this equation and found out that B square minus A square equals to 64. We use the algebraic identity here that B square minus A square equals to B plus A times B minus A, that is equal to 64 according to equation number 1. So here it is given us the question that AC and BC are integers. AC equals to B and BC equals to A according to our definition. So B and A will be integers. And we know that A and B are the lengths of the right triangle, therefore there must be a positive number. So from those two facts we can derive that A and B are positive integers. Okay? And we know that B is positive integer and A is positive integer. Therefore B plus A must be greater than B minus A, because when you add two positive integers to each other, the result must be greater than the situation that you subtract the two positive integers by each other. So B plus A must be greater than B minus A. And we know that B is the hypotenuse, and the hypotenuse is always greater than the perpendicular, so B is greater than A. We subtract A from this equation and we get that B minus A equals to is greater than 0. So B minus A is a positive number, B is integer and A is integer, and B minus A is a positive number. So B minus A must be also a positive integer. So I found out that B plus A is a positive integer and B minus A is positive integer, and we also know that B plus A must be greater than B minus A. So I wrote down all the possibilities that we have that the multiplication of two positive integers by each other will give us 64. The first possibility is 164, the second is 232, the third is 416, the fourth is 88, the fifth is 16,4, the sixth is 32 and 2, and the last one is 64 times 1. So, because we found that b plus a must be greater than b minus a, it means that the first column must be greater than the second column. So which rows we have that the first column is greater than the second column? We have here 16 is greater than 4, 32 is greater than 2, and 64 is greater than 1. So we have only three possibilities for the values of b plus a and b minus a. Then we added the two numbers together. Here b plus a, we added to b plus a to b minus a, so it is b plus b, that is 2b, and a minus a is 0. So we actually arrive to the conclusion that if we add the two numbers together, we must get an even number, because 2b is even number, b is a positive integer, therefore 2b is an even number. So here 16 plus 4 is 20, that is an even number, so this is a good possibility. 32 plus 2 is 34, this is also an even number, so this is a good possibility. But 61 plus 4 plus 1, 64 plus 1 is 65, this is an odd number. So this possibility will get cancelled because the result is not an even number. So we are left only with two possibilities, that b plus a equals to 16 and b minus a is 4, and the other possibility is that b plus a is 32 and b minus a is 2. Okay? So we wrote down here the two possibilities. In order to find out the values of b and a themselves, b plus a is 16 and b minus a is 4. And the second possibility is b plus a is 32 and b minus a is 2. So in the first possibility, we added the two equations together. B plus b is 2b, a minus a is 0, and 16 plus 4 is 20. We found out that 2b equals to 20. We divided this equation by 2 and found out that b equals to 10 units. And here, according to this equation, b plus a is 16. We subtracted b from this equation and we found out that a equals to 16 minus b, but we already found out that b equals to 10 units. So a equals to 16 minus b, and b is 10, so a equals to 16 minus 10, that is 6. So in conclusion, we found out that the perpendicular a equals to 6 units, and the hypotenuse b equals to 10 units. Here, the perpendicular b equals to 6 units, AB is 8 units is given as the question, and the hypotenuse b equals to 10 units. According to the second possibility, we added the two equations together. B plus b is 2b and a minus a is 0. 32 plus 2 is 34. In conclusion, we found out that 2b equals to 34. We divided this equation by 2 and we got that b equals to 34 over 2 is 17. Okay, the hypotenuse b is 17. Then we have this equation that b plus a equals to 32. We subtracted b from this equation and we found out that a equals to 32 minus b. But we have already found out that b equals to 17, so we substituted b by 17 and we got that a equals to 32 minus b, that is 17. 32 minus 17 is 15. So in conclusion, we found out that here a equals to 15 units and the hypotenuse b equals to 17 units, and it is given as an equation that a equals to 8 units. So those are the two right triangles that will be the solutions for our question inside each triangle we have a circle that is inscribed by the triangle, and we want to find out the radius of this circle that is inscribed by the triangle. Okay, so in order to find out the radius of the circle that is inscribed by a triangle, we actually draw a general right triangle. Triangle ABC could be any triangle here. Inside this right triangle, triangle ABC, that could be any triangle, we have this circle with radius R. This is the center of the circle. We define side AB as A. We define side BC as B. And we define the hypotenuse AC as C. And then we have here AB is tangent to the circle at point M. BC is tangent to the circle at point M. So, according to rule number 1, whenever we have a radius that is drawn to the point of tendency, AB, tangent AB will be perpendicular to the radius NO. So this angle equals to 90 degrees and this angle also equals to 90 degrees. Here we have the radius OM that is drawn to the point of tendency. Therefore, according to rule number 1, tangent BC will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. So in quadrilateral ONBM, we have 3 right angles, 1, 2, 3. And we know that the sum of the angles in any quadrilateral is equal to 360 degrees. So the sum of 3 angles, that is 270 degrees, plus the size of the 4th angle, must be equal to 360 degrees according to the rules I mentioned. So this angle must be also equal to 90 degrees. In order to complete the sum of the angles in quadrilateral and OBM to 360 degrees, this angle must be equal to 90 degrees. So we actually found out that quadrilateral and OBM we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral and OBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. But NO equals to R, therefore BM must be also equal to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. OM equals to NB, but OM equals to R. We already found out that OM equals to R, therefore NB must be also equal to R because they are equal to each other. So in conclusion, we found out that quadrilateral ONBM, it is not a rectangle but a square because all of its sides are equal to each other, they are equal to R. Then we found out the length of line segment AN. From the drawing, it is very easy to see that AN equals to AB minus NB. AB is A, NB is R, so AN equals to A minus R. Then we found out the length of line segment CM. CM equals to BC minus BM. That is to say, CM equals to BC, that is V, minus BM, that is R. So in conclusion, MC equals to B minus R, and AN equals to A minus R. Then I presented to you rule number 2, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So if you focus on the common standpoint point A, the common standpoint point A, we have 2 tangents to this circle, tangent AN and tangent AC, and according to rule number 2, they are equal to each other. So AN equals to AC according to rule number 2, but we have already found out that AN equals to A minus R, therefore AC must be also equal to A minus R because they are equal to each other. Then we focus on the common standpoint point C. From the common standpoint point C, we have 2 tangents to this circle, tangent CM and tangent CL, and according to rule number 2, they are equal to each other. CM equals to CL. But we already found out that CM equals to B minus R, therefore CL that is equal to CM must be also equal to B minus R. So in conclusion, we found out that CL equals to B minus R and AN equals to A minus R. Okay, and so the hypotenuse AC equals to AL plus LC. The hypotenuse AC equals to AL plus LC. From the drawings, it's very easy to see it. AC equals to AL plus LC. AL equals to A minus R, and LC equals to B minus R. AL equals to A minus R and LC equals to B minus R. And according to our definition, AC, the opposite AC equals to C. So we substituted AC by C, AL by A minus R, and LC by B minus R, and found out that C equals to A plus B minus R is minus 2R. So C equals to A plus B minus 2R. We added 2R to this equation and found out that the 2R plus C equals to A plus B. We subtracted 2R, we subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that I equals to A plus B minus C over 2. Here are the radius of this circle that is inscribed by the right triangle ABC equals to A plus B, that is the sum of its perpendiculars, minus the hypotenuse that is C over 2. So this is a general formula to find out the radius of any circle that is inscribed by right triangle ABC. Therefore, we can implement this formula in our two triangles. Okay, so I write down the formula here. This is the formula that we found, and we implemented the new formula in our two right triangles. Because it is true, this formula is true in any right triangle. Triangle ABC could be any right triangle, and in any right triangle that blocks a circle. Okay? So in this right triangle, we get that the radius of this circle that is inscribed by this specific right triangle, triangle ABC, will be equal to A plus B, that is the sum of its perpendiculars, that is to say 8 plus 6, minus the hypotenuse that is 10 over 2. 8 plus 6 is 14, and 14 minus 2 is 4. 4 over 2 is 2. So we found out that the radius of this circle that is inscribed by triangle the right triangle ABC equals to 2 units. Then according to the second possibility, we have here R equals to A plus B, that is to say 8 plus 15, minus the hypotenuse that is 17 over 2. 8 plus 15 is 23, and 23 minus 17 is 6. And 6 over 2 is 3. So we found out that the radius of this circle that is inscribed by this right specific triangle ABC equals to 3 units. So here we actually found out that we have two solutions to the question. The radius of of this circle that is inscribed by the right triangle ABC, it could be 2 units or 3 units. Okay, that is the answer to the first question. Okay, then I presented to you the second question, and we solved the second question in 2 different methods. Here we have this quarter circle. AOB is a quarter circle. Inside this quarter circle we have the right blue triangle DCB. You know that side OB equals to 2 units. And we also know that AD equals to DO, and we want to find out the area of the blue right triangle DCB. So in order to find out the area of the right triangle DCB, so first of all we know that in any quarter circle, angle AOB equals to 90 degrees, and the radius is OB, that is 2 units, and the radius is also AO. So here we can write down that AO equals to OB, and AO also equals to AD plus DO. Okay? Yeah. AD plus DO equals to AO, that is equal to OB, equals to 2 units. It's the radius of the quarter circle. So we define AD as x, so DO will be also equal to x because they are equal to each other. So in conclusion, we found out that x plus x, that is 2x, equals to 2. We divided this equation by 2 and found out that here AD equals to 1 unit and DO is also equals to 1 unit. Okay? Then we completed the quarter circle to a circle, and we extended side CD by a straight line until it touches the circle. Suppose that it touches the circle at point X here. Then we'll get that we created here a peripheral angle that is equal to 90 degrees according to what is given as the question. And we know that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. But if the touching point of the extended CD with this circle is at this point, point X, it means that this peripheral angle that is equal to 90 degrees is not, doesn't rest on PB, that is the diameter of the circle. So we have here a contradiction. Therefore, in order to solve this contradiction, we must arrive to the conclusion that when we extend the side CD by a straight line, it must touch point P. It must pass from point P. In this way, we get that this peripheral angle PCB that is equal to 90 degrees indeed rests on the diameter of the circle that is PB. Otherwise, we get that we have a peripheral angle that is equal to 90 degrees that doesn't rest on the diameter of the circle. That is a contradiction. And so in order that peripheral angle PCB will rest on the diameter, side CD must pass from point P. Okay, and here we have so PB is the diameter of the circle because it passes from point O, that is the center of the circle. This angle equals to 90 degrees, so this angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of the straight line PB to 180 degrees. This angle must be equal to 90 degrees. Okay? Then we implemented the Pythagoras theorem on this right triangle and found out that this angle equals to square root of 5 units. We implemented the Pythagoras theorem on this right triangle and found out also that the hypotenuse is equal to square root of 5 units. We extended side AO by a straight line until it touches the circle at point Z. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle that is equal to 2 units according to what is given as the question. Then I presented to you rule number 1 that if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We actually can implement rule number 1 in our drawing because in our drawing we have chord AZ that intersects with chord CP at point D. Chord AZ intersects with chord CP at point D, therefore we get that AD times DZ equals to CD times DP. Again, AD times DZ equals to CP times DP according to rule number 1. AD times DZ equals to CP times PD. AD equals to 1. Here, DZ equals to 1 plus 2, that is 3. CD is the missing line segment. And DP equals to square root of 5 units. So in conclusion, we found out that 5 equals to CD times square root of 5 units. We divided this equation by square root of 5 units, and we found out that CD equals to 3 over square root of 5 units. Here CD equals to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right triangle, the right blue triangle CDP. Here, and we found out that in the right triangle CDP, BD square equals to DC square plus CB square. BD is square root of 5, so BD square is 5. DC is 3 over square root of 5, so DC square is 9 over 5. Plus BC square, that is the missing line segment. We subtracted 9/5 from this equation and found out that 5 minus 9/5 equals to CB square. We multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression. So we found out that 25 minus 9 over 5 equals to CB squared. 25 minus 9 is 16, and 16 over 5 equals to CB squared. We took out of this equation and found out that CB equals to the square root of 16, that is 4 over square root of 5. Here CB equals to 4 over square root of 5. So we have here all the sides of the right blue triangle DCP, therefore it is very easy to find out the area of this right blue triangle DCB. The area of this right blue triangle will be equal to the base of the triangle, that is CD, times the height to the base, that is CB, over 2. This is the base times the height to the base, that is CB, over 2. This is 3 over 5 square units. CB is 4 over 5 square units, all divided by 2. 3 times 4 is 12. Square root of 5 over 5 is 5, all divided by 2. So here 12 over 2 is 6. So in conclusion, we found out that in the denominator we have 5. In conclusion, we found out that the area of the blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finished with the first method. Then I presented to you the second method. So we already found out that the first method, that this angle equals to 90 degrees, or B AD equals to 1 unit, DO equals to 1 unit. We completed the quarter circle to a semicircle. We extended side BO until it enters the circle at point P. O is the center of the circle, P is the point of the semicircle itself. Therefore, PO is the radius of the semicircle, that is 2 units, according to what is given as the question. We have already found out that PD equals to the square root of 5 units, and OB equals to the square root of 5 units. According to the first method, we define angle DPO as theta. Angle DPO equals to theta. Angle DOP equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles to 180 degrees. Likewise, in the right triangle PCB, this angle equals to theta. This angle equals to 90 degrees. So this angle must be equal to 90 degrees minus theta. Then we proved that the right triangle POD is similar to the right big triangle PCB. Why those two right triangles are similar to each other? First of all, we have those two angles that are both equal to 90 degrees, therefore they are equal to each other. We have those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. And we have this angle that is a common angle, it belongs to both triangles, so this angle equals to itself. So we actually proved that all three angles of the right triangle POD can go into all three angles of the right big triangle PCB. Therefore, the right triangle POD is similar to the right triangle PCB according to angle similarity rule. And from the fact that the right triangles are similar to each other, we derive that PD over PB equals to CD over CB, that is equal to PO over PC. PD equals to square root of 5 units. Here PB equals to 2 plus 2, that is 4. DO equals to 1 unit. CB is the missing line segment. PO equals to 2, and PC, here PC equals to square root of 5 plus DC. Okay? So from this long equation, we created the first equation, the square root of 5 over 4 equals to 1 over CB. We cross-multiplied this equation and found out that square root of 5 times CB equals to 4. We divided this equation by square root of 5 and we found out that CB equals to 4 over square root of 5 units. Here CB equals to 4 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle CBD. On the right blue triangle CB, BCD, according to the Pythagoras theorem, dB square equals to DC square plus CB square. So dB is the missing line segment. We leave it as it is. Or dB equals to actually to square root of 5. So dB square is 5. This is the missing line segment, so we leave it as it is. CB, here CB equals to 4 over square root of 5, therefore CB squared will be equal to 16 over 5. Okay, so in conclusion, we found out that 5 equals to DC squared plus 16 over 5. We subtracted 16 over 5 from this equation and found out that DC squared equals to 5 minus 16 over 5. Here we multiplied 5 by 5 and then we divided it by 5 in order to have a common factor of this expression. And we found out that 5 times 5 is 25, so it is 25 minus 16 over 5. 25 minus 16 is 9, so we have here 9 over 5, that is equal to DC squared. We took a root out of this equation and found out that DC equals to 3 over square root of 5 units. Here, DC equals to 3 over square root of 5 units. We found out all the sides of the right blue triangle, triangle DCB. So the area of the right blue triangle, triangle DCB will be equal to the base of the triangle that is DC times the height to the base that is CB over 2. The base is DC times the height to the base that is CB over 2. DC is 3 over square root of 5 units. CB is 4 over square root of 5 units, all divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5. All divided by 2. 12 over 2 is 6. In the denominator we left only with 5. So in conclusion, we found out that the area of the blue right triangle, according to the second method, equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay, so in both methods, we found out that the area of the blue right triangle, this blue right triangle, equals to either 6 over 5 units, or in terms of numbers, it is equal to 1.2 square units. Okay, thank you very much.